Welcome to topic 24, central limit with proportion. All right, so the previous topic is about central limit theorem with simple mean. So here we're going to talk about this thing called the simple proportion. So let's, to explain this, assume students in our class are the population. And let's say Mr. Chen randomly select 15 students and 12 students favor dropping the lowest test grade. So the population proportion P, okay, that's what lowercase p stand for, of students in favor of dropping the lower test grade would be 12 out of 15, which is 0.8, 80%. So um, a while ago, I mentioned the word proportion. Proportion also means the word percentage. Okay, also basically derived from the relative frequency. All right, so population. So every time when I say the word proportion, I'm also referring to as the word percentage. So there's about 80% of students favor dropping the lower test grade. All right, so the population proportion P is the fraction or percentage of the population that has certain characteristic. Okay, and the formula is given by X. X is the number of individuals in the population that have certain characteristic divided by the total population size. So the characteristic here is 12 students favor dropping the lower test grade. All right, a sample proportion. Okay, so when we're taking small samples of these percentages, okay, is given by P hat. This is called P hat, which is the number of individual in the sample has the same characteristic divided by the sample size. Okay, so the sample proportion is called P hat. Population proportion is called P. All right, when the sample taken are simple random samples, the condition for a binomial distribution are met. Okay, this is very interesting. We talked about binomial distribution before, and the sample size are large enough to ensure that the sample size times the population proportion P is greater than or equal to 5. And the sample size times 1 minus P, remember when we talk about binomial, 1 minus P is also Q. Okay, is also greater than or equal to 5. A normal distribution can be used to approximate the binomial sampling distribution of the sample proportions. Okay, with the mean and the standard deviation given by, all right, the population mean of your P hat is going to equal to the true population proportion. Okay, so again, every time I use the word proportion, I mean average, right? I mean, that's the word average. Excuse me, that's the word percentage. The standard deviation of your sampling proportion P hat is equal to square root of your population proportion times 1 minus P, or you can say Q, divided by, okay, sample size. So to find the standard score, here is our formula. It's basically P hat minus the mean of the P hat divided by standard deviation of the P hat, the sample proportion, which we know we can say the standard, which we know that the mean of the P hat eventually becomes the population P. Standard deviation P hat is equal to this. So here I make a note, the difference between sampling distribution of your sample mean X bar and sampling distribution of the sample proportion P hat is one uses percentage, P hat uses percentage as random variable, and X bar uses sample mean as random variable. Okay, so let's take a look at these examples. Okay, so these are a very similar step as the one that how we find probability of the sampling distribution of the sample mean. So let's say suppose 40% of the population has Crohn's disease. If a random sample of 455 is selected, what is the probability that the proportion, okay, so that means percentage, that the proportion of the sample person with Crohn's disease will be less than 34%. Okay, so we know about 40% of people has Crohn's disease. So when we take a sample of 455, okay, out of that 455, what's the probability that the percentage of the people of the 455 will have Crohn's disease that is less than 34%? So this 34% is the sample proportion coming out of the 455. All right, so let's list a population proportion. So the mean of the p hat will eventually equal to population proportion p, which is 40%. All right, your sample proportion p hat is 34%, 0.34. And the sample size 455. All right, find the z-score. So I'm gonna copy this down, okay? I'm gonna copy this part down. So the z is equal to, all right, the p hat minus the true population proportion divided by square root of p times 1 minus p or q divided by n. So it's easier to figure out what 1 minus p is here. Okay, so if p is 0.4, 1 minus p got to be 1 minus 0.4, which is 0.6. So 0.34 p hat minus the p divided by square root of p is 0.4 times 1 minus p is 0.6 divided by n is 455. All right, so I'm gonna put the numerator in a parenthesis. All right, divided by, I'm gonna put an entire operation denominator in a separate parenthesis, okay? Square root of multiplication, then divide, right? 0.4 times 0.6 divided by 455. So if you type in just like this, calculator knows it will multiply then before it will divide. All right, I close the parenthesis for the square root. I'm gonna close the parenthesis for my entire denominator. If I round to 2 decimal place, that's about negative 2.61. All right, probably. So the area I'm looking for, less than, means area to the left. So use normal CDF. Okay, looking for the area to the left. So the left bound is negative infinity, negative 1E99, comma, negative 2.61, comma 0, comma 1. So let's put it in the calculator. All right, the percentage 0.0045. So out of the 455 sample we took, the probability that less than 34% will have Crohn's disease is not even half of a percent, right? 0.004 is about 0.45%. Okay, let's try another one. So let's say, suppose 45% of doctors in the hospital are surgeons. In a sample of 457 doctors, what is the probability that the sample proportion of surgeon will be greater than 39%? Okay, it'll be more than 39%. So the 39% is my p hat. This 39% come from the sample 457. All right, so the mean of the p hat of the sampling proportion will eventually equal to the true population proportion, which is 0.45. The sample proportion, okay, is 0.39. Sample size 457. All right, so z-score again, p hat minus p divided by square root. Gotta be very careful, okay? What's inside the square root is p minus 1 minus p divided by n. So p is 0.45. So 1 minus p got to be 1 minus 0.45, which is 0.55. So 0.39 minus 0.45. divided by square root of 0.45 times 0.55 divided by 457. All right. Minus divided by, okay, open a parenthesis for the whole bottom, square roots of 0.45 times 0.55 divided by 457. Close parenthesis for the square root, close parenthesis for the whole entire bottom. Okay, that's about negative 2.58. So greater than 39%. So that will be looking for the area to the right. Okay, so that's a lot of area. Negative 2.58 is right here. How many percent? What's the probability that will be more than 39%? Okay, well, our doctors. So that's a lot of area right there. So normal CDF. All right. Left bound negative 2.58, comma. Right bound is positive infinity 1E99, comma 0, comma 1. So if I put this in the calculator, let's see. One E99, comma 0, comma 1. It's about 0.9951. Okay, about 99.51% chance. Okay, that that the surgeon in the proportion will be more than 39%. Okay. So there are 99.51% chance, okay, that the surgeon will be greater than 39% of them out of that sample. Okay, so just real quick, kind of introducing how we can use central limit theorems with proportions, but with a little bit of binomial in here, because because think about the Crohn disease, right? Either you have Crohn disease or you don't have Crohn disease. Okay, so that's the reason why we can actually use, okay, the condition for binomial are actually met. Okay, the condition for binomial are met when n times p and n times q is greater than or equal to 5. So make sure the sample size got to be large enough in order for this binomial distribution, condition to be set. All right. So a normal distribution can be used to approximate the binomial sampling distribution of the sample proportion. All right. So just kind of real quick talk about how we can use central limit theorems to talk, for the sampling distribution of proportions. All right. So there's only one homework problems here, okay, which is very similar on the one that we just did. All righty. Thank you for watching.